Hi everyone, this is the video for your graphical analysis example. And really my goal for this example was to just get you recognizing and thinking about the different pieces that you can analyze when you are trying to form a conclusion. So your data sets, regardless of if you collected them, if you were given them, if you researched them like I did with this one, you're still going to be looking at some of those same pieces to make those conclusions. And one of the main things that you're going to look at is going to be your mathematical model, which we know we have to form. And the only way to form the model is to graph it, see what type of relationship it is, and then kind of go from there. But some of the other things that you want to do is what I have in the directions here. So briefly explain, what does the slope represent? So what does it mean in real life? There is a much bigger meaning to slopes in science than there is when you're just purely doing a math equation. You get, okay, we know that it's the change in y over the change in x, it's the rise over run, whatever you want to call it. We know that it's a rate of change, but in science, that rate of change has a much, much, much bigger meaning. Same thing with the y-intercept. That is a physical piece that has a true real life representation, and we want to try to figure out what does it mean. So my goal of this example is to just kind of get you exposed to and thinking of some of the different questions you should be asking when you're given a data set and what you should do with those different pieces once you get to the model. So as soon as you're given a data set, the very first thing you should say is, okay, well, what can the data by itself tell me? And typically the biggest thing that it could tell you is this going to be a direct or an inverse relationship? So we know that if it's a direct relationship, both the x and y variables are either going to increase or decrease at the same rate. If they're an inverse relationship, as one increases, the other decreases. So if we look at our volume, we see that we start at 48, but we go all the way down to 17. So we're decreasing for the volume and the pressure is clearly increasing. So right off the bat, we know that we are dealing with an inverse relationship. And that automatically tells us, hey, I need to linearize because right now I'm not in y equals mx plus b. So we go ahead and pop over to our graphical analysis section or Google Sheets, I apologize. And we see once we graph it using all of our good graphing techniques, putting in our titles, putting in our units, we do indeed see an inverse relationship. But maybe you're looking at that and saying, well, maybe it's a negative linear. I can't tell. So we know that one of the tools in our toolbox is to double click and we can go ahead and add a trend line. So if we go to customize and we go to series, we can go to trend line, and right now it's a linear trend, but it only has an R squared value of about 95%. So it's a little bit under. So looking at that, you're like, well, it's not horrible, but is there something better? Because that's only saying that you're only about 94.7% accurate for this trend line. However, if we put in an exponential, now we're getting 98.7. And if we put in a polynomial, we'll look at that. We see the 99.6%. So that is our clear indicator. Hey, this is a much bigger accuracy than if it was a linear trend. So we know it is going to be that inverse relationship. Now, what you should be starting to think about at this point is what does it mean to be an inverse relationship? Why is one increasing and why is one decreasing? And one of the reasons why I chose this is because you need to think back to chemistry for this question. Oftentimes, especially when we're dealing with our data sets in class, we have to be thinking about, okay, well, what previous background knowledge do I know and how can I apply it to what I'm looking at right now? Background knowledge from chemistry tells me that the ideal gas law is PV equals nRT. So if you were to isolate the P and the V portion, we know that that pressure and volume is an inverse relationship because of Boyle's law. So this whole lab that was conducted by UPenn actually proved Boyle's law and it proved the ideal gas law. So one of the conclusions that we can make about this, knowing our chemistry background, is that this was an ideal gas that was tested on. So that is why we are seeing the inverse relationship, is because it's an ideal gas and it's going to follow the ideal gas law. So that's kind of a lot to kind of digest at first, but it is what we're going to have to do. We will have to pull background information from chemistry, math, other things that we learn in physics, and apply that to what could this new data set be telling us. So that's kind of one conclusion that we could make, and that is a big conclusion. Realizing that this was a gas and realizing that it proved the ideal gas law is indeed a big conclusion. Now, we do still want to form our model. So we know that in order to linearize, we have to do 1 over the x. So for my title, I'm going to do 1 divided by volume. And I do the same thing for my units, so 1 divided by liter. And then pressure is just going to stay the same. So I'm going to let Excel do the work for me. So equals 1 divided by A5. Enter. And I'm not going to want all of those decimal places because I am not accurate to that decimal place. We're only about accurate for the first 2 decimal places. That's typically what we stick with in physics. And then I could just go ahead and copy this over. All right, so next thing I would want to do is go ahead and insert my new chart. Let's go ahead and actually move this over so that I can see my numbers. There we go. All right. And go ahead and add in our X series. Or I'm sorry, our Y series. There we go. Scatter. All right, now we get a beautiful linear trend, which we can work with. So the next pieces that I would want to add in this, I would want to put in all the titles, put in all the units, but for the sake of time in this video, I am just going to jump right to forming the equation. So one of the things that we can do is we can either calculate the slope by hand, or we can just take the slope from Excel. So if we go ahead and put in our label as use equation, this is now in the y is equal to mx plus b form. All right, so we have y equals mx plus b, but we know that we put in what y represents, so we have pressure is equal to 1409, and then we say, okay, well, we have to have units here, so that's going to be the units for what we actually graphed, so we have pressure divided by 1 over liter. Now, at this point, you can go ahead and simplify that if you would like. I also would be fine if you just left it in the complex fraction for now. Yeah, either one is fine. All right, so then we have to multiply by 1 divided by volume. And then we add in our y-intercept, which is 0.0197. And we have to put in those units, so that is going to be pascals. Now, if we think about that, we do have a very, very, very small y-intercept. Most likely what this is going to represent is probably a little bit of error. Especially with true data collection, there is a very small amount. So 0.01 is most likely just a little bit of error that was conducted as they did the lab. But that is extremely, extremely minimal and not something that we would discredit the findings for. I'm sure even if we put in our R-squared value, yeah, we're getting an R-squared value of 1. So we could chalk it up to a little bit of error. We can also just say, hey, that was the minimal amount of pressure that they needed in order to start the lab, or that was already within the container. So that's what you want to be doing when you see these numbers. We want to say, okay, what are the possibilities that this could represent? So it could be a very small amount of error. What most likely is the answer is that it was the small amount of pressure already contained. Now for this one, the slope, that's really something that we would want to look at a little bit more. If we were to look at that full ideal gas law, what other pieces are contained within the PV equals N nRT, and how did that nRT kind of get factored into this? And that's where we would have to look at and say, okay, well, temperature should have been held constant. So now we're just left with moles and that R value. And that's what you would want to start to discuss in this final conclusion piece, is how does the ideal gas law and this kind of come together to form one large conclusion. Now, every single problem will not be a chemistry problem, but it will run the same way, where you have to, first, let's look at the data. What does it tell us? Now, what does the trend tell us? Now, what does the linear trend tell us? And what does the model tell us? So those are the four big pieces that you want to really look at when you're forming a conclusion. All right, you have your on your own problem now.